All right, welcome back, everybody. Before I switch to writing, I wanted to show you, we have I don't know if you guys know this. There's a building over near the main COS campus called the Giant Marketplace. It's COS, where is it? There it is. And it's not always open. They have limited hours if they're open, but they have free food for students, like grocery supplies and shit like that. I saw it was open. On my way out of class today, I immediately pulled in, got out, asked them if I could film what it was like in there. So like people could know, like. If you don't have a lot to eat at home and you're struggling to make ends meet, that's not helping you in your education. It also sucks. But like COS offers this, they actually offer information on and resources for housing, transportation, more. I have flyers up here for it while I was there. The guy was super excited that a teacher like gave a shit. And so he gave me like, you want some flyers to give out? If any of you are interested, come up after class if you want to grab one. And you can check out the website. This is like literally like me walking through the place for like a minute and a half. This is in our module section, in the orientation section. It's the bottom one. So you can come check it out at your own leisure. I know people don't like looking like they don't have money. So I'm not gonna make anybody watch anything here or ask questions about it here. People are like very insecure about it. It sucks. It's a shitty thing that our society does. Makes people that with low income feel bad for having low income. So we have resources available if you're in need of food and stuff. The school also does something called Giant Threads. I want to say it's once a semester you can get a free suit, like a suit that you can wear for an interview. It may not have a jacket, but it'll be like a button up and slacks and then nice shoes, or if you're a lady, an appropriate blouse and slacks, or I think you have the option of dresses, however you choose to dress. Whatever your dress style is, they have something for you, and it's once a semester. I'll get information and share that with you guys as well. But I've seen the Giant Marketplace open, so I went and made a little video. All right, let's go back to covering what we're gonna cover today. What the fuck? Got that shit chopped.
I had too much, man.
You had that mullet going on strong.
Yeah, I was committed to the bit.
Yeah,
I did it.
when someone's got that long hair going and all of a sudden it's gone, it's noticeable. It's not like my wife when she's like, I got my hair cut. I'm like, was I supposed to notice what you get a half inch or some shit? Was it just the fucking split ends? How am I supposed to notice that shit? I don't know, she fucking manages to notice. I tend to wait though too. I don't let it get to where you had it, but like, this is getting long already. But I'm sure it'll be another month before I drag it and go get my ass in to get a haircut. And then I'll have a nice little flat top going on. It's immediately noticeable. Alright, let's do some math here. Where were we? We were gonna talk about 6.3 today. And I'm gonna start a little bit at 6.5. 6.3 is on the graph of sine and cosine. (6.4) does the sine cosine in hard mode. And we're gonna do that on Tuesday. So please do some of the fucking homework for 6.3 before class on Tuesday. It's 5 days away, you've got time. Don't drag it off, put it off. At least do some sine, some cosine, that way you'll understand. Like it'll be easier to follow through for 6.4. If I have time, I'm gonna start 6.5, which is on tangent and cotangent, which have similar ideas to 6.3 and don't require like super knowledge. So we're gonna start 6.3. Sine and cosine graphs. So all of the trig functions All trig functions are in a group called periodic functions. Periodic functions repeat. After a certain interval. For example, what is cosine of 0? It's 1. What is cosine of 2 pi? One. What's cosine of 4 pi?
Oh, 1. This is a circle.
It's a circle, so every time we go around the circle, we're 0. We go all the way around, this is 2 pi again. We go all the way around, we get to 4 pi again. The value repeats. And in fact, that's the only point on there that has a 1. That's why I chose that one. In fact, it's the same thing goes on with sine and cosine. If I did sine of pi over 2. Sine of pi over 2 is the straight up. Sine represents the y value. Sine as pi over 2 is 1. If I add another 2 pi to it, 2 pi plus pi over 2, which is 5 pi over 2, it's also 1. If I add another 2 pi on that, so 4 pi plus pi over 2, or 9 pi over 2, I'm at 1. It's a period, this is a periodic function. And so periodic functions in general can be written like this. F of x is going to have the same value of f of x plus n times p. P is the lowest value it takes to start repeating. N represents number of repeats. What I wrote with sine and cosine, can you tell what P is?
0.
How, what do I need to add to the inside to make it start repeating again? 2 pi. I added 2 pi here, I added another 2 pi here, I added 2 pi there, I added 2 pi there. P, which stands for the period, for sine and cosine, is 2 pi. Can't start right there. Someone just took their test today with the AAC, I didn't get it yet, so I'm handing out tests on Tuesday. You'll have a great episode. I keep procrastinating because Gerardo keeps pressuring me. So he's making me procrastinate. I don't like these bullies. He's not bullying me. Grab the unit circle because we're gonna strip values from it in a second. Let's go through and blast through this unit circle again real quick. Does anyone need this up longer?
Yeah.
Alright. We're gonna blast through the unit circle real quick. That way I'll have it there to grab from and pull from to reference.
Looking at it again.
Keep looking at it until you don't need to look at it. Keep practicing it until you don't need to. I still got blanks, so if you wanna. You want more copies of the like to practice on. Having those memorized, like you need it memorized for the test. But like having it memorized is going to help you so much. In all of your later math classes, because you're not gonna have to slow down and grab a calculator. When other students that aren't bullied by the teacher and memorizing the shit. And you should have, it's just simple memory. It's not rocket science. I know, I've done rocket science, this is not the same. Rocket science uses it though, rocket science uses this shit a lot, uses trigonometry a lot. It's at angles, everything goes that travels at an angle. Or then we go into, you've got to start orbiting shit, now you got a circular pattern or an elliptical pattern. There's things that go around and angles pop in and. So I guess it is rocket science. But it's just the baby steps of rocket science. Alright, anyone need that longer? Alright, let's power through this. It says. Place the degree angle measure of each angle in the dashed area. So let's go through that real quick. This is 0 degrees, pi over 2, pi, 3 pi over 2. And we get back around, we're at 2 pi. The diagonals are your ones that have a 4 on bottom. So pi over 4, 3 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. These are, remember it goes 2, 3, 4, 6. So the ones on this angle are the 6s. This is pi over 6, this will be 7 pi over 6. This will be one less than that, 5 pi over 6. And this will be one less than 12 pi over 6 would be 11 pi over 6. Then we do the pi over 3, 2 pi over 3 over here, 4 pi over 3 over here. And 5 pi over 3 right there. Those aren't degrees, those are fucking radians. Look at me saying put the degrees there. Now, if you do this shit, because this is the first page of your test without a calculator. If you put the degrees on the radian line and the radians on the degree line, I'm not gonna be an asshole. Clearly, it's easy to fucking do. Right? It's easy to fucking just get distracted. As long as you're consistent with it, I'm good. Let's put the degrees on the other one. 0, 30, 45, 60, 90. Slap some degree symbols on those. That's 180 degrees, 270 degrees, 360 degrees. Here you got 120, 135, 150, 210, 225, 240, 300, 315, and 330. Then you go through and do the X and Y. Remember, these parentheses are X and Y, and we're putting in cosine theta, sine theta. They also match up with graphing. So like 1 point over, this is 1, 0, without even knowing cosine and sine. If I did a graph on an XY chart, it's that. This would be 0, 1. This is negative 1, 0, and this is 0, negative 1. This is where all the other fun shit comes in. The one I always remember, the one I use my go-to is sine of 30 degrees, because it's easy to remember. There's no fucking radicals in it. It's 1/2. And then I remember that the 1/2 goes with a √3/2. And as this goes up, we get a bigger square root on top. And as the cosine goes up, we get a smaller square root on top. That's the first quadrant. Everything from there has symmetry. Those are the ones you gotta remember. If you can remember that and remember reference angle is off of x-axis, never off of y, you're good to go. These mirror over. This would be 1/2 √3/2, √2/2, √2/2, and √3/2, 1/2. But in quadrant 2, on an XY graph, why is it so bright? On an XY graph, X is negative over here, X is negative here, Y is negative here, and Y is negative there. We just gotta change the signs of our X values. Negative, negative, negative. And now we reflect them down here. √3/2, 1/2, √2/2, √2/2, and then 1/2, √3/2. Down here, X and Y are both negative, so that's why sine and cosine are both negative down there. And then quadrant 4, you can reflect across this way or across this way. √3/2 right here, 1/2, √2/2, √2/2, and then we got 1/2 and √3/2. Over here, X is positive and Y is negative, so we're throwing the Y's are negative and bam, done. It's a simple pattern that it follows. The hardest thing to remember is, to be honest, the degrees. Because the degrees don't have as much of a noticeable pattern as the radians do. The radians have 6s on these diagonals on bottom. They have 4s on these diagonals, and they have 3s on these diagonals. The degree doesn't have anything like that. So it doesn't, there's a pattern to everything but the degrees. We've covered that before. I'm gonna keep that available. If you're still writing, go right ahead back. If you are writing, let me give you a couple minutes to finish it. Can't hurt. And that's proof that you can go through it in 5 minutes, because not only do I go through it in 5 minutes, but I was explaining what I was doing while I did it, which slows you down. It can be done, it's just practice. It's like you learn basic addition by practice. Hopefully you know your multiplication table. Not everybody does, like up to 10 by 10. They used to teach that in elementary school, I don't know if they still do. There's evidence to indicate that that's not being taught anymore. From some students not knowing the multiplication table. But I'm not gonna put anybody on blast, hopefully you know that. Alright. So, how do we go through and graph some of this stuff? What we're looking at is y equals sine x. And then we'll graph y equals cosine x. But what that means, this will be next page. Cosine. What this means is like our x, our theta is being replaced by x. which allows us to graph it on an XY chart. We'll do this since we're doing sine. I'll have that right there so we can see it right there. In fact, that might be even better. A little bit. Sine is our y value on these coordinates. What is the lowest y value and the highest y value for sine? Remember, y is your up and down, so we're looking at the bottom of the circle and the top of the circle. -1 and +1. Which means our graph can only go from -1 to +1 up and down. How often is it 0? Like, where is it 0? Where does the y value look like 0? Remember, we're looking at the y value. We got a y value of 0 here at 0. We got a y value here at pi. We're not gonna use degrees. When you're graphing, you're using radians with it. Graphing is radians only. If you put x equals 30, 30 is a number, not a degree. So we gotta use radians since x is a number and not a degree. So our 0, where y equals 0 occurs at, it looks like 0, pi, 2 pi. It's every pi. Every time it hits the x-axis, it's at a 0. And this is true going the other direction, -pi, -2 pi, -3 pi. So if you put some good amount of space in there. Let's say that's pi, 2 pi, 3 pi. I'll try to do the same spacing going the other way. And zeros in the middle, these are all 0. For the sine graph. Where did these ones occur at? And -1. What radian value? Pi over 2 was our 1, right? Pi over 2 is halfway between pi and 0. That work for y'all? Because pi over 2 is 1/2 pi. In fact, I can go through and add in other increments here. And I'll go the other way. And put those in there. Pi. So we said. At pi over 2, it was 1, so we could put a dot at pi over 2 and 1. Does that make sense? Does that match up with what we got? Pi over 2, if I plug that in as my degree, I get 1 for sine. Yeah. And if I plug in 3 pi/2, I get the -1. Right, so I could do -1 down here. What happens if I go around the circle and I get back up here again? What radian am I at up here again?
2/2. Or
2
Zoom
pi
around.
plus pi/2.
Yeah, plus.
So the next step would be for the 2 pi plus pi/2. If I multiply that by 2/2 to get a common denominator. I got 4 pi plus pi/2, so 5 pi/2. Looks like it's back up to 1 right here. And if I subtracted 2 pi, it would be over here. I don't even know if I'm at this, it looks like my elevation's changing. No, that looks good. -1 has that same repetition too. I could add 2 pi to it. 2 pi to this would basically add 4 to the top. And it would be 7 pi/2, which is kind of like off screen. But I could go the other way and it would be at -pi/2. And -5 pi/2. Now, it looks like it kind of is like from what we have so far, it looks kind of like a lightning bolt. But if we look at this 30, 60, 90, let's see what's happening. When x is 30 degrees or pi/6, which is effectively breaking the, that would be pi/4. And that would be 3 pi/4 if I just keep writing those in half. If I break up this region into 3. I would have like pi/3 right there. Or pi/6. And then 2 pi/6, which is like pi/3 is right there. Pi/6 is 1/2. So it gets to the halfway point right away. Then at 45 degrees, which is where pi/4 is, it's a little bit over. It's √2/2, which is about 0.7. And √3/2 is. Yeah, that sounds about right. I'm just fucking brain farting.
It's a guess, so.
That's about right, yeah, 1.7 inch cut in half. So it looks like it's not doing a lightning bolt, it's doing like a curve. And that curve does the same thing coming down the other way. And it follows that pattern, it doesn't go straight to it. It makes this rolling curve. And this just looks really high because I made my 1 really high to emphasize it, generally it looks flatter. It also goes the other direction. We can keep going. The base curve that is really important to memorize. Is from 0 to 2 pi for sine. In fact, we're gonna note the important parts to remember here. 0 to 2 pi, because if I look over another 2 pi, I have the exact same wave. It starts off high and it goes down low. Starts off high, goes down low. Starts off high, goes down low. So if you remember 0 to 2 pi, you just rinse and repeat. So 0 to 2 pi is the. I'm gonna call it the base period. For sine. of theta. It seems like the most important ones, at least for plotting, as long as you remember it does a wave and not like a jig-jag lightning bolt. The most important points to remember for plotting is the top and the bottom. That seems pretty important, right? And where it crosses the x-axis, the zeros. So the important points to remember for graphing important points for graphing sine. And it turns out this will be true for cosine as well, but they just have different values. We want 0. We want pi over 2, pi, 3 pi over 2, and 2 pi. That's my x value. And my y, which is sine x, it goes from 0. It went up to 1. It's back down to 0. At 3 pi over 2, it's -1 and 0. If you remember those 5, this will be for the base. We're going to learn to make adjustments to it. 4 adjustments. Graphing is easy. Is easier. There's some fun things going on with sine that I need to mention here, just so you have a little more information to go with it. We like to note what the domain and range are. Remember, domain is all possible input or x values. And for sine, it doesn't look like there's any problem. I can keep this wave just keeps going on. So the domain is negative infinity to infinity. Range is all possible output values. And that's your y. The lowest value was -1 and the largest value was +1. And since we include those, we use brackets. We mentioned this before, the period is 2 pi. The x-intercepts, where it crosses the x-axis. These are also called the zeros of the function. We noticed it was at 0, pi, 2 pi, 3 pi, 4 pi. It's at every multiple of pi. And we have a handy way of writing that. We say they are at n pi. Where n is an integer. I really don't like the name integer, it's confusing to a lot of students. So as a reminder, integers are your positive and negative whole numbers. And 0. That's not positive or negative, so. And for the final one, I kind of want to show you it. How do sine of -pi/6, how does that relate to sine of pi/6? Not flip. What do you mean by flip? Well, what do you mean by flip? The sign flips. Sign flips, okay. So like sine of -pi/6 is -1/2. And this is 1/2. So I could say sine of -pi/6 equals negative sine of pi/6. Does that seem fair? This actually is true for any x. Sine of -x equals negative sine of x. For all x. And when that occurs, when a function has that, we call it an odd function. And the usefulness of that isn't gonna show up for about at least 6 months. Till you're a good halfway through Calc 1. Maybe, no, near the end of Calc 1. So you're like, it's near the end of Calc 1. Odd functions are really, they make calculus easier. If you know an odd function or an even function, you can take advantage of certain calculus traits. But you maybe won't remember odd and even by then, but hopefully. You'll look back and go, Mr. Jones said something about one of these being odd and one of these being even. Cosine is gonna be an even function. Now let's look at cosine. Let's cover some of this boring shit right here, right now, before we get to the graph. Domain is negative infinity to infinity. And range is -1 to 1. Period is 2 pi, just like sine. It's intercepts. If we look at our unit circle, it happens at pi over 2, because we're looking at cosine, which is our x value. It happens at pi over 2. 3 pi over 2. If I go back around, it's 5 pi over 2. 7 pi, oops. 7 pi over 2. And we can go the negative direction, negative pi over 2. Negative 3 pi over 2, stuff like that. The way they write this in shorthand notation is n pi plus pi over 2. Not the screen. There's another way to write this, and just like where I got a common denominator right here, the same thing happens here. If I multiply this by 2 over 2 and factor out a pi, well, if I don't factor out a pi, before I have to multiply by 2 over 2. If I factor out pi, I have n plus 1/2. And oftentimes they just multiply this by 2 and say 2n plus 1 times pi. All of those are the same versions of what's going on here. This one doesn't have any fractions in it, which is kind of handy. Wait, that's not right. Gotta have the fraction somewhere. It just doesn't go away. And you'll notice that we do the cosine of negative pi over 6 and compare to cosine of pi over 6. These are both √3 over 2. You'll find that if you stick in a negative x for any value of cosine, you get the same thing as cosine of positive x. They call this an even function. And it doesn't show you why odd or even. Odd or even actually comes from, I don't know if you learned it in algebra, so I'm gonna gloss over it here real quick. The normal odd functions are y equals x, x cubed, X to the fifth, X to the seventh, X to the ninth. Your even functions, when there's no trig involved, is y equals x squared, x to the fourth, x to the sixth, x to the eighth, x to the 10th, so on. The exponents are odd or the exponents are even. What's really gonna bake your fucking noodle, and it's not gonna happen until like the latter half of calc 2, is we can write sine functions as a sum of a bunch of these exponent or x's where they have an odd exponent, and we can write cosine as a bunch of x squared, these things added up, but with different coefficients. It's really neat. That's why they can do a lot of stuff musically in terms of math. Music travels as a sound wave, and these are waves. So you can match up a wave, that's what this sine graph is, it was made a wave. So cosine does the same thing, and you can match that up to music, and music match. You can match that up to music, you can match it up to math, this is a graph. They do some cool shit. Let's take a look at that graph. Does anyone need that part of owners?
You got it. But
MF. Come on, fucking screen. How long have I been on screen?
you just pressed it.
Okay. Okay, let's go look at the graph of this real quick, and then we'll take a break. So I told you the important points to remember are 0, pi over 2, pi, 3 pi over 2, and 2 pi. These are the values on the x and y axis. And they are the x values. The one on the left. It starts at 1, goes to 0. At pi, it's -1. At 3 pi over 2, it's down to 0. And at 2 pi, it's back up to 1. So if I graph this. Let's do this right here. At my multiples of pi, I'm either at 1 or -1. I start high, I go low, and I'm back high again. You're asleep. I see it. That's right. I don't know about you guys, the fucking, it's not that loud, sometimes it's super fucking loud. The fucking, do you guys ever like fall asleep to the sound of a fan? I fucking love, like, it's my white noise. I started doing that shit when I was like 8, and my mom, like, we were in Sacramento, and in fucking summers it was hot, and we didn't have AC. It was fan, she let us have a fan in the bedroom, she'd go in there and fucking turn that shit off. And she thought we were asleep, and we would be asleep. But it would fucking wake me up turning it off, and as soon as she was gone out the room, I'd wake up, fucking turn that fucker right back on. Cause and I've been that way since I've been a kid and child. Alright, and now at my in-between points, my pi over two and 3 pi over two. Pi over two, I'm at 0. So it looks like it's doing the wave like this. God, that looks terrible. That's my base wave. Base wave right here. Base period or base wave. And if I repeat that, I can keep doing multiples of pi over two in each direction and just keep following that pattern. As long as you have a couple of them labeled, you actually don't really need to label the rest because people can figure it out. We go low or middle, low, middle, high. And it follows a nice rolling wave. I wish Bob Ross would have taught this shit. It would have been called happy waves. Then we go the other way, starts high, goes middle, goes low, goes middle, goes high. I think my spacing got a little bit off over here on the right. It's gonna start looking compacted some. Let's take a 10-minute break and we will come back and look at some slight adjustments to this before we talk about tangent. What happens to my y values if we use y equals 3 cosine x? What? Multiplying by 3. So this goes up to 3. 3 times 0 is just 0. This is negative 3. This is 0 and this is 3. And I need a bigger graph. Try to keep my spacing the same. Zero is staying in the same spot. Right? 0 is still 0, but everywhere that was a 1 is now a 3.
Isn't that like shrink factor or shrink or expand?
This is yeah, it's a shrinking kind of thing. Shrinking or expansion. This is an expansion. We'll do shrinking in a second. And the ones down there do this. So it still has a wave, but now it's got much bigger hills and valleys. It still crosses the x-axis at the same point. That point was in the wrong spot. And I could do this over here. So that's my y equals 3 cosine x. Emma. I know. Felt it, I heard it there. I was about things there. Yeah, just totally just fucked off Gerardo and other students, just like,
I'll drink.
well, now you got a second to get back on the train. And rather than making a new column, what happens? If y equals 1/2 cosine x. It's flatter, right?
Yeah.
All the ones become 1/2s. It does some shit like this. So that number in front, if I do something called, if I say like y equals a cosine x. And this, it happens with sine x too. In fact, it happens with all of them, but it's most noticeable with cosine and sine. A affects the height of the graph. And we call it amplitude. Now. I was gonna say drums don't count, but they do. Every musical instrument, depending on which string you hit and what stuff like that. The amplitude is really like how hard you hit the string or bang the drum. But like the note you get changes where these points are. They're not necessarily 0 to 2 pi. It either makes the wave shorter or longer, which we're gonna look at in a second. But just like music, when you play a bunch of different instruments together, you hear different things. Waves add together like that. And so that's why we can add a bunch of things together, and it's how music works. This is how a music synthesizer works. They take the waves and they put them together, add them up, they treat them as a wavelength like this. And they add the waves like that, because it's digital, a lot of them are digital, it's not like they're plucking a bunch of fucking strings, getting the sound. Collectively, sine waves and cosine waves are called sinusoidal waves.
They're together, right?
Yeah, they're both sine and cosine or sinusoidal waves. Anything that does this flowing up and down like a gently rolling hill. Tangent, cotangent, secant, cosecant don't look anything like this, so they're not in the sinusoidal wave category. In fact, is it the Beatles? Might be Hard Day's Night. One of the Beatles songs. There's a ding right at the beginning, and there's a bunch of instruments hitting the same similar note at once. And they thought they knew who was in the recording studio, but when they decomposed the waves using math and shit, they realized there was a fourth musician in the room that wasn't given credit. I forget who it was. It was someone like associated with the Beatles, but like there was a note in there from another instrument that was not like acknowledged in the soundtrack. Because they did some math shit on it and were able to, each instrument has its own signature. Strings, obviously, you can't really see it that well because they're vibrating so fast, but they make little waves. the surface of a drum, if you slow it down in fucking very slow motion. It does a wave outward from where you hit, but it goes out in all directions. Not just along a string where it travels along the line, you do a guitar or a violin. The string vibrates up and down like these waves. A drum does it in a radial, like radiates outwards in these waves. And it's really hard to see the little up and down, but like they've done slow motion of drums, it's kind of really neat to look at.
So it's harder to see the drum?
Yeah, it's pretty hard to see. Cause it's like drums tend to be, well, all instruments are really taut, that's why tight strings, that's why it works well. But like. It's easier to notice the string because you can see it from the sideways. And it's a lot harder to see a drum that way unless you have a glass drum. Where you can see through the side, because you're looking at the up and down on the surface, and normally you're looking at the drum from above, that's some sort of angle. The string, you're actually, like, the way you pluck it, you're looking at it from the side. And if you take physics, they'll go into it. So that's amplitude, that affects both sine and cosine. But there's a way to make the wave shorter. So if we have a number on the inside, I'm gonna use B, because they tend to use B. I'm gonna show you by example why it works, rather than just tell you, that way maybe it'll make more sense. If I have y equals sine of 2x. And I still want to plot. Where's my sine graph? Not right there, where the hell did I put it? There's my important points. I still want to hit my 0, 1, 0, -1, and 0. Let's say I still want to hit those. What do I gotta plug in to get the same values here? So what I'm really trying to ask is, this is like theta here. And I want my, and these are like theta here. I want to get, for this to happen, I still need pi over 2, pi. Wait, I'm off by 1. 0, pi over 2, pi, 3 pi over 2, and 2 pi. But if I plug that in for x, well, that's gonna work on 0. But if I plug in pi over 2 for x, 2 times pi over 2 is what? 2 times pi over 2 is just pi, which puts me down here. So what do I need to plug in? What x value do I need to plug in so that I end up with pi over 4? If I could just set it. You take half of pi over 2. Half of pi over 2 is pi over 4. We just showed that this is doing 2 times pi over 2 gets me the pi. What do I need to plug in to get 3 pi over 2 if I'm multiplying it by 2? Everybody trying to do it with intuition.
6 pi.
6 pi over 4? I don't know. Shit.
Pi over 6.
Let me show you an easier way to realize this rather than guessing. If I don't know what this value is, I could call it x. And I'm aiming for a particular target over here. How would I find out what x is in algebra? How do I get x by itself? Divide by 2 or multiply by 1/2? We're doing that here. If I divide or multiply pi over 2 by 1/2, do I get pi over 4? Pi over 2 times 1/2 gets pi over 4. If I multiply pi by 1/2, I get my pi over 2, that's good. So what do I need to do, multiply by? If I do 3 pi over 2 and I multiply by 1/2, what value goes in that box? 3 pi over 4. And the same thing with the 2 pi. I multiply it by the 1/2 and I get pi. So my first value was 0. My last value is pi. The period, our base period for y equals sine or cosine of 2x has shifted. It started from 0 to 2 over pi. And it shifts to 0 over pi, or 0 to pi. In fact, if I don't use 2, if I just use bx, what I did here is the same. I just have a b in front rather than a 2. So I'm gonna multiply by 1 over b instead of 1 over 2. We're trying to undo the thing multiplying on x. Notice going from here to here is effectively like multiplying by the 1/2 that we saw up here. So the base period for bx does the same thing. We're going to multiply this by 1 over b, and it goes 0 to pi over b. Let's do another one with like 3x or better yet. Let's go with 5x. Let's do with this with 5x, do the same process, get the values. That way you can kind of see, like get a, like I've seen a lot of pages that are like a little fuzzy on it. Let's look at the same process with like 5x. I'll do cosine instead. Now the cosine one starts at 1. It went 1, 0, -1, 0, 1. I'm going to do 5x equals 0. I'm just solving each of these. 5x equals pi over 2. 5x equals pi. 5x equals 3 pi over 2. 5x equals 2 pi. That's what I did up here. So if I want to figure out what x is for each one, I think this is easier if you treat it as multiplying by 1/5 rather than dividing by 5. Because then it's like multiplying fractions. I get x equals 0 there, that's good, that stays the same. This is pi over 10. Multiplying each of these by 1/5. Now I want to show you something because it might help you do your graphing for these. Is anyone confused with the math there? Multiplying fractions, not all of them have a fraction. There's not a fraction, you can put pi over 1 to make it a fraction. And then you multiply tops and bottoms separately. Now, this is a real pain, and you're like, where the fuck are these on the graph? Right? If I multiply this by 2/2 and this one by 2/2. This is now 2 pi over 10. This is 4 pi over 10. The one between them is 3 pi over 10. And that one is effectively 1 pi over 10. That's a little easier to graph. Because I don't need to go, where the fuck is pi over 10 in relation to pi over 5? Like, comparing these two on the graph in my head fucks me up. But if I know where 2 pi over 10 is, 1 pi over 10 is half the distance to the goal. Right? Half the distance to 0. So, if you, when you're graphing these, if you convert them all to the. This is effectively. Our b here was 5. If you write them all with a denominator of 2b. Denominator, I hate fucking spelling this word. Of 2b. Then all of your points, your 0, your pi over 2, your pi, your 3 pi over 2, your 2 pi, they all shift to 0 over 2b, 1 pi over 2b, 2 pi over 2b, 3 pi over 2b, 4 pi over 2b, every single time. And that makes graphing this by hand really easy. You get a sec to write this down. This has got a kind of a nice easy pattern to follow, kind of like the pattern we follow with the angles, right? The top is just a multiple of pi, and the bottom is just 2 times b. Whatever's on the inside double. Check out how easy this is to graph by hand. Hold on, I need to wait a second. Let me finish filling out that table. We had pi over 5. 3 pi over 10. And 2 pi over 5. But this is better off as that column. Yeah, graphing this where you like will definitely need the x and the y value to be the same was already a pain in the ass. Because pi is 3.14, so it doesn't fall on a nice little grid line. Neither does pi over, none of the fucking angles in radians fall on a nice little grid line. So this was never friendly to graph on x or y. If you do it on Desmos, there is a way to shift it so it does the x-axis in terms of radians. Which is pretty good. I gotta look up, remember how to do it. But here, we're gonna do y equals cosine of 5x. And I'm gonna show you how to graph this the easy way. Okay, your basic xy axis, where the x-axis, the positive x-axis is longer than the y-axis. And make 4 evenly spaced marks. Four evenly spaced marks on x-axis. The 0/2b is just 0. I'm gonna write this part below it. This mark is always gonna be your 1 pi over 2b. This one will always be your 2 pi over 2b. This one is your 3 pi over 2b. And this is your 4 pi over 2b. In our case, for cosine of 5x, so it's pi over 10, 2 pi over 10, 3 pi over 10, and 4 pi over 10. I'm kind of trying, I'm writing them where they're trying to put them where they're not in the way of my graph. The y value hasn't changed, there's no amplifier here, or amplitude isn't changing. So we know we're gonna go from 1 to -1. And cosine starts high. Sine starts at the middle. That's just an easy way to remember it, rather than remembering the ones, like those are the values, but. Cosine starts high, cosine starts up here. And then all you gotta do is remember the wave, it makes a wave. So it goes down. And then it goes back up. If I went the other way, it would be a little bit more like that, and I continue this. I'm gonna put y equals sine of 5x on the same graph. To illustrate something kind of. Be sure everyone's got the cosine graph in first. We can draw right on top of that motherfucker and. Sine started in the middle. It went high and then went back down. I aimed better. That's as easy as graphing that shit gets. Now, if there's an amplitude on it. Make the graph taller or shorter as necessary. For example, if I did y equals 2 cosine 5x. Find the x values first. Using that shit. And then do height accordingly. Cosine 5x. Cosine 5x. Sine of 5x. He said, this is way back, chapter 1, chapter 5, whatever the fuck it was. We said sine of theta is cosine of theta minus 90 degrees. Or plus 90 degrees. Okay. No, minus. We could also treat this as cosine theta equals sine of theta plus 90 degrees. I'm not sure. That's why this blue line and this red line look like the same wave, they're just shifted. Now, here they're off by pi over 10, not 90 degrees or pi over 2, but that's because we did the 5x, not regular x. You look at y equals sine x and y equals cosine x, they're the exact same wave. Sine and cosine look like the exact same wave, they're just shifted a little. Kinda neat. If you guys want to work on, and then we'll do together. But I wanna try to lock this in real quick without doing it for you. Try graphing y equals 1/2 sine of 3x. We'll do it together, because we're running out of time. Get to change it like I thought it would. This part of it, the B part is the hard part. Most people are cool with the amplitude, you're like, yeah, you just make it taller. Yeah. So what is my points gonna be? What's the bottom of my fraction? 6, right?
Yep.
And that's the equivalent of 2 pi/3 if I reduce the fraction. So. And if I put 1 there and -1 there, I'm only gonna go to half the height. Right? If you do them all evenly spaced and you just show the first mark what the value is. It can be reasoned that everyone after that is just a multiple of that. Does that make sense? Cause like when we do what, like this was 1, this is 2, 3, 4, you're just adding to it. The idea here is we can literally get away with showing that. I'm gonna leave it at that for now. But know that this matches up with pi/6. 2 pi/6. 3 pi/6. 4 pi/6. Sine starts where? Middle. And which direction does it go, up or down? Up. We're only going up to 1/2. This was also 2 pi/3. So that makes like this one pi/3. I'm gonna overlap this with sine of x, 1/2 sine of x, just to illustrate something. 2 pi/3, if I evenly space it, that would be 3 pi/3, which is pi. 4 pi/3, 5 pi/3. 6 pi/3, which would be 2 pi. If I do y equals 1/2 sine of x. Let's see where this is 3 pi is about there. Halfway between 0 and, sorry, pi/2 is right about there. It's doing this. Got to hit down there. Up, middle. I'm not going far enough out. And back up. That is 1/2 sine x. If we keep repeating this wave. What's gonna happen? Where this is y equals 1/2 sine 3x. The red graph did 3 full cycles. While the green graph did 1. That number here, that 3 right here, tells you the amount of, another way of looking at it is how many times that graph is gonna repeat in a regular cycle. Sine of bx, b tells you how many times the graph will repeat. Over 0 to 2 pi. You'll find when b is less than 1, like if b is 1/2, it takes longer. You don't get a full cycle in. All right, it's 5 o'clock. The torture will continue on Tuesday. Please have tried this, because then we're gonna look at using the same stuff. And we're gonna start doing, they're called translations. Adding stuff to the equation both inside the parentheses and after the parentheses. That causes the graph to move left and right and up and down. And it's like, if you haven't practiced some of these. That shit, you might as well not even show up, honestly. If you haven't done any homework, any of these problems by Tuesday. You're better off not coming to class, because it's just gonna confuse the shit out of you. You're better off watching the video later. You know what I mean? I will see you guys on Tuesday. Have a good weekend. And I am at the Mason Center on Saturday if you're interested.